gentlemen, today's class recording has begun, so watch what you say if you don't want it saved for posterity on the internet forever. Okay? All right, yesterday we started talking about the idea of quantum numbers. And quantum numbers are meant to help us interpret this diagram that we drew on Thursday of last week. What did we say this was a diagram of? This is a bunch of orbitals, right? And what is our definition of an orbital?
Place where electrons can occur.
Place where electron can occur, although we might say it's a place where electrons are most likely or probably going to be, all right? This picture, the idea of an orbital, is based on the work of two scientists. What are the two scientists who helped contribute to this picture, right? Heisenberg and Schrödinger, right? So Heisenberg in his uncertainty principle said that we'll never know the exact location of an electron, but Schrödinger said we can figure out a probable location based on where those electrons have been in the past. Okay? All right. Good? Good. Okay. Yep. Yesterday, we introduced the first two quantum numbers. Yesterday, I kind of introduced a quantum number sort of using an analogy. What is a quantum number as it describes that orbital? It's kind of like an address, right? It's a description of a location. But just like your address, that doesn't necessarily mean that we're going to find electrons there, but it describes a location. How many total quantum numbers do we have to describe each orbital and distinguish it from all the other orbitals? 4, right? Yesterday we introduced 2 of them. What was the name of the first quantum number that we introduced yesterday?
That's not a number.
It's not a number.
0.
What is the name of the first quantum number that we introduced yesterday? Andrew?
S.
The principal quantum number. Okay? So, as it says up on the board, what letter do we use to represent the principal quantum number?
Lowercase n.
Lowercase n. And basically, the principal quantum number describes 2 things about the orbital. And those 2 things are related to each other. So what does the principal quantum number describe about that orbital, generally speaking? Mo. The energy level, which is related to what? How close the orbital is to the nucleus, right? So the bigger the principal quantum number of an orbital means that it's located farther away from the nucleus. And that means that if electrons are in that orbital, they will have more energy. All right? Good for the first quantum number that we did introduce yesterday? Okay. What was the name of the second quantum number that we introduced yesterday? Mo, you want to go? No. What was the name of the second one? The angular momentum quantum number. All right? So, like it says up on the board, what letter do we use to represent the angular momentum quantum number? L, lowercase l, so a lot of times I'll draw it like this cursive L, okay? And generally speaking, what does the angular momentum quantum number describe about an orbital? The shape of the orbital, okay? So we see up on the board, right, that there are 4 possibilities for the angular momentum quantum number. First, if we assign an angular momentum quantum number to an orbital of 0, that means it's an s orbital. What do all s orbitals look like? They're spherical, okay? Regardless of how far away they are from the nucleus, if an orbital is spherical, we call it an s orbital. All right? The next shape we run into is a p orbital. Generally speaking, what do p orbitals look like? Those are going to be like hourglasses. Regardless of how far away from the nucleus this hourglass orbital is, if it's an hourglass shape, we refer to it as a p orbital. Okay? And then we talked a little bit about d orbitals. We said d orbitals are kind of like our butterfly shapes, right? And f orbitals are just too crazy to really draw, so don't worry about those, okay? Good for starters, okay? All right. As it relates to our drawing, right, we started assigning quantum numbers to these different orbitals that we drew in our picture on Friday. So we started off with the first two quantum numbers. This was the first orbital that we drew, the one that's closest to the nucleus. First, we assigned it a principal quantum number of 1 because it's the closest it's the closest to the nucleus that we can be. But then we assigned the angular momentum quantum number equal to 0 because this is a spherically shaped orbital. So we start off, in terms of an address, started building the quantum numbers that describe this orbital. We started off with these two. And then the next one we started looking at was this one. And so we talked about the idea that when I'm switching colors, that's essentially switching principal quantum numbers, okay? So this one we went from the yellow spherical orbital here to the red spherical orbital here. That increased the principal quantum number from 1 to 2. So that's why n is equal to 2 for this orbital. But it's still spherically shaped. And so the angular momentum quantum number, we still assign a value of 0 because all spherical orbitals get a principal quantum number, or sorry, angular momentum quantum number equal to 0. And then the next spherical orbital that we came across was this blue one, all right? It's spherical, that's why the L value, or the angular momentum quantum number, is still 0, but because it's farther out from the nucleus, the principal quantum number is equal to 3, all right? And I think somebody asked about this one, right? Okay, and so here, because this is still a spherical orbital, the angular momentum quantum number would still be 0, but because it's one more layer outward, the principal quantum number would be equal to 4. Okay? Good? Okay. Then, so we went from here to here, right? This was the first hourglass-shaped orbital that we drew. Because it's the same color, the principal quantum number is still equal to 2. N is equal to 2, just like n was equal to 2 for this red orbital. But the shape is different, and that's why we assigned a different angular momentum quantum number. All p orbitals get assigned an angular momentum quantum number equal to 1. Regardless of what color or what energy level they're in, they get L is equal to 1. Okay? And so we talked about this one, and then I think, if I remember correctly, apparently we didn't draw these in, right? But if we're talking about this orbital specifically, right? It's a p orbital, right? Remember, this is the whole thing like this, yeah, okay? It's a p orbital, and that means that its angular momentum quantum number will be equal to 1, but which energy level is it in?
3.
The third energy level. So here, we would give it a principal quantum number equal to 3 because all blue orbitals are in the third energy level. Okay? Good? Okay. But right at the end of class yesterday, we ran into somewhat of an issue, right? So we assigned these two quantum numbers for this p orbital, right? And we talked about the idea, right, that this is one orbital, okay? But then the next orbital that we drew was this one, right? This is still an hourglass shape. It's still a p orbital, but it's along the y-axis instead of being along the x-axis. But if we're assigning quantum numbers, it's still red, so that means n is equal to 2, and it's hourglass shaped, it's a p orbital, so that means L is still equal to 1. But if you compare the quantum numbers for this orbital with the quantum numbers for this orbital, they look the same. All right? So we have to find a way to distinguish these two orbitals from each other. All right? And that brings us to the third. Actually, let's do this. On your outline, I think we filled in the Roman numeral number 1 and Roman numeral number 2, I think, correct? Yeah? Okay. And then we also filled in Roman numeral number 3, but then we jumped ahead to Roman numeral number 5, yes? Okay. All right, so let's fill in Roman numeral number 4 because it relates to sort of Roman numeral number 5. I think next year I might change it, but you guys are stuck with this one, okay? So the angular momentum quantum number describes the sublevel within the energy, or within the principal energy level. So each principal energy level has sublevels. Each color has different shapes that are the same color. We call those different shapes sublevels. The first sublevel in each PEL stands for principal energy level, is S. Every time we switched a color, what was the first shape that we drew? Circle. Actually, it's sphere, right? But the first shape that we drew in any color is always a sphere. That's the S sublevel. Okay? But how many circles did we draw in each color? Only one, right? The first thing we drew when we switched colors was the sphere, but we only drew one of them, okay? So there's only one s orbital within each level of the atom, okay? The next sublevel that we run into, okay, there are, right? Okay, so they're all spheres, right? 1s, 2s, 3s. We just keep getting farther away from the nucleus, okay? But then, the next one we run into is the p sublevel. And we said that p orbitals look like hourglasses, but how many p orbitals did we draw? How many hourglasses did we draw in each color? 3. One on the x-axis, one on the y-axis, one on the z-axis. So good. Yep. Yeah. Oh, so for s orbitals, right, for the spherical orbitals, we said that L always gets assigned what number for those s orbitals? 0. Okay? And then p orbitals always get assigned an L value equal to 1. Okay? But, as we said, or as we saw in our drawing, the first main level that we drew was yellow. But how many yellow orbitals did we draw in our entire picture? Just one. There's only an s orbital in the first level. It's really small, it's really close to the nucleus. So go ahead. Yep.
Why is the y-axis listed green?
Depending on, like, so it's just different orientation for that book compared to other things, right? So if you talk about 3 dimensions, right, 1, 2, 3, I should do it this way. Stand by. Okay. So if this meter stick represents the x-axis, right, and then this meter stick represents the y-axis, okay, this is what you're familiar with from math class, right, okay, and then we add the third one in that looks like this, okay. So here, x is horizontal, y is vertical, and z is front to back, right? But let's say for whatever reason this atom twists, so now it looks like this, okay? So what we called the x-axis before is still horizontal, but the one that we called the z-axis is now vertical, and the one that we call the y-axis is now front to back. Does it really matter which one we call x, y, or z? As long as they're different from each other, that's all we really kind of need to know. So like in your pictures are like, that's basically just tilted 90 degrees so that y, instead of being up and down, is now front to back, and z is up and down. As long as we can tell one from the other, that's all that's really important. Okay? All right, good on the p sublevel. Okay, these are our hourglasses. So the next one that we run into, okay, so those are p orbitals, right? And just like your chart shows, right, we have 3 of those p orbitals, one along the x, one along the y, one along the z. Whenever they show up, there's always 3 of them, all right? And then finally, and then if we put them all together, they look like this, okay? And then finally, the next one we run into is our d sublevel, okay? And we said that d orbitals kind of look like those butterflies, right? But we didn't start drawing butterflies until we got to the blue orbitals in our picture, right? So d orbitals don't start showing up until we get kind of far away from the nucleus. And then there's a 4th sublevel that's called F, but that's just too much for us to draw on, so I'm not going to worry about too much about that one, okay? All right, good. So going back to, let's go back to this picture, right? This picture over here on the right shows the 3 p orbitals that would exist, like in, let's say this is the 2nd energy level. So these are all 2p orbitals. But we got to be able to tell one from the other if we're describing the orbitals, right? Your address, even though your house, like if you like live in a development where one builder built all of the houses, your house might look pretty similar to the house next to you, or the house 2 houses down, or 2 houses down from you. They all might look similar, but we got to tell them apart somehow, right? Your address is specific to your house. So even though these are hourglasses in the same energy level, or they're all the same color, we got to be able to tell one apart from the other one, okay? So that brings us to the 3rd quantum number that we call the magnetic quantum number, okay? So the magnetic quantum number indicates which orbital this electron is in within each sublevel. We use the lowercase letter m to represent the magnetic quantum number. And in terms of a description, it tells us if we have multiple p orbitals, which p orbital are we talking about? Or if we have multiple d orbitals, which d orbital are we talking about? Okay? Yes, sir? Yeah, we're missing one. I'm going to show you right now what that means, because it's a little confusing, okay? Are we good with what the magnetic quantum number is describing for us? Okay? We have orbitals that look similar. If we look at, go back to our picture right here, right? This orbital is a p orbital in the 2nd energy level. This orbital is a p orbital in the 2nd energy level, and this one is also a p orbital in the 2nd energy level. So we got to be able to tell these 3 apart. Okay? All right. So the one spot that's missing on there, it says that possible values run from -L to +L. -L to +L. Okay? -L to +L, and I'll explain that to you guys in just a second. Okay? All right. Good with the values, or good with the stuff on the outline. Couldn't think of what you guys were supposed to fill in there. So. Good with that? Okay. So let's go back to this picture. Okay? Let's go back to this one for starters. Okay? So, we've got our first 2 quantum numbers. Okay? And then the 3rd one, we just learned, we use the lowercase letter m to represent the 3rd quantum number. All right? We learned that the angular momentum quantum number, L, for any spherical orbital gets assigned a value of 0. But for m, we said that it runs from -L to +L. So -0 to +0, how many options do we have there? -0 to +0, right? There's only one option there, right? It's what? 0. Because how many s orbitals are there in each color? Only one. So we don't have to tell this s orbital apart from other s orbitals. Too much there. So anytime that L is equal to 0, M is equal to 0 as well. Because there's only one s orbital. So we don't have to tell it apart from any other s orbitals. Okay? Yep. So any sphere where L is equal to 0, M is going to be equal to 0 as well. Okay? Because that's the only possibility for an s orbital. There's only one of them, so we don't have to tell them apart. Okay? The M value, the magnetic quantum number, starts becoming important when we start adding p orbitals. Okay? Are we good that the first two quantum numbers for this orbital and this orbital are exactly the same? You okay with that? Okay. So now, that's where the magnetic quantum number comes in. Okay? The magnetic quantum number, we wrote in our outline, says it runs from negative L to positive L. What's L for a p orbital? 1. So if we go from negative L to positive L, that means our options are negative 1, positive 1, but what do you have to go through to get from negative 1 to positive 1? 0. So M for p orbitals can be negative 1, positive 1, or 0. Okay? How many total p orbitals can we have in each color? 3. X, Y, and Z. So, well, so Connor, if we look at your outline, so go back to page 3 of your outline. I think I sort of where we filled it in there. What did I say M was for the x-axis? Okay, so here I'm going to label the magnetic quantum number for this axis negative 1. Okay, but then the next orbital that we drew was along the y-axis. Okay, so here we're going to give this one a magnetic quantum number equal to 0. And now we have a difference between the quantum numbers for this p orbital and for this p orbital. Okay, so if we were to put quantum numbers on this third p orbital here, first, it's still red. What does that mean about its principal quantum number? 2. It's a p orbital, so what does that mean about its angular momentum quantum number? 1. But if we look at the previous 2 p orbitals, right? This one, we gave the magnetic quantum number m a value of negative 1. We gave this p orbital a magnetic quantum number equal to 0. So what does that mean the magnetic quantum number for this one has to be?
1.
Not just 1, but positive 1, right? Okay. And now, even though we have 3 p orbitals that are exactly the same color, have we distinguished all of them from each other?
Yeah.
Yeah, right? They have their own combination of numbers. Okay? Good there?
Yeah.
Okay? So, just to hammer that point home, let's go here, right? Okay? Here's a p orbital in the third energy level. These are the first 2 quantum numbers that we use to describe this p orbital. But when we add the third one, so which axis is this p orbital on? The x-axis. And if you look in your notes, talked about that this orbital would have a magnetic quantum number of negative 1 because it's on the x-axis. Okay? Connor, go ahead.
What if you're doing
magnetic number for the butterfly.
Hold on 1 second, we'll get there. Okay. So that means this one, right? It's blue. What does that mean about its principal quantum number?
3.
N equals 3. What shape is it? It's an hourglass. That means it's what kind of an orbital? A p orbital. And that means that the angular momentum quantum number is equal to 1. And which axis is this p orbital running along? The y-axis. And I think in my notes, I assigned magnetic quantum number equal to 0 there. Following me? Okay. Connor, here we go. Okay, so here's a d orbital, right? Remember, d orbitals are butterflies, right? Even though it looks like 4 separate locations, this is all one orbital. Okay? All right, here we go for this orbital, for this d orbital. First, what color is it? Blue. Say purple, that's cool, right? All right, so it's blue, right? What does that mean about its principal quantum number?
3.
All blue orbitals have exactly the same principal quantum number, so that n is equal to 3. Okay? All right, now something different. We said that butterflies, we give, or what is the name of the butterfly orbital? It's a d orbital. Okay? And all d orbitals, regardless of where they show up, we assign an angular momentum quantum number equal to 2. All right, here we got to do some interpretation. Okay? What are the possible values for m for this d orbital? Chris? -2 to +2. So that means it could be -2 or -1 or 0 or 1 or 2. How many possibilities do we have for m for d orbitals?
5.
5. And if you look back on your chart that is in your notes on page 2, how many d orbitals are there?
5.
5. Is that a coincidence?
No.
No, not a coincidence. You have to tell these 5 apart from each other, okay? Now, here we can get a little bit creative, okay? This is the first d orbital that we've drawn. So what could m be? What could the magnetic quantum number be for this d orbital in particular? Could be -1, or it could be -2, or it could be 1 or 2, or have we drawn any other d orbital? No. So at this point, we can give this one any one we want. Let's call it -2. Okay? At this point, yeah, well, any of those 5, Connor, right? It's got to be -2, -1, 0, 1, or 2. Okay? Because remember, m values are -L to +L. Does that make sense? Okay? But then, when we draw this second one, right, which is this one right here, okay? N is 3, L is 2, because it's a d orbital in the 3rd energy level. M. There's only one value that m can't be for this orbital. It can't be -2 because we called the other one -2. So we could call this one what?
2.
Call it 2. We could call it 0 or -1 or whatever we want to, as long as we don't call it -2, because the other one was -2. We got to make them different from each other, right? So we could call this one +2 if we want to, or whatever, as long as it's different. Okay? Does that make sense? Hey. All right. Last quantum number. Last quantum number is called the spin quantum number. We use, spin is actually really easy, everybody. It's the easiest one, okay? All right, so spin, we use the lowercase letter s to represent the spin quantum number, okay? And it's really easy because all of those shapes that we drew on that picture are called what? Orbitals. Orbitals are possible or probable locations for electrons. What's true about every single electron? How are they similar to each other? They all have a negative charge. Will we find many electrons in each orbital? Okay, no is the correct answer. Why don't we find too many electrons in each orbital? They start getting too crowded and they repel each other. All right? So each spot, each one of those shapes that we drew on that picture only holds a limited number of electrons. Because if we start putting too many electrons in there, they start repelling each other and they don't like that. The maximum number of electrons, did I say minimum before? Whatever. Oh, I said limited, that's what I said. The maximum number of electrons that each orbital can hold is 2. And we call that idea the Pauli exclusion principle. Wolfgang Pauli is another scientist who worked on this kind of stuff, okay? We'll explain this a little bit more tomorrow. And that means that the spin quantum number only needs 2 values. And we use +1/2 and -1/2 to represent those 2 possible values. Okay? So hold on, we're almost done. So let's go here, and let's go back to our very, very first orbital. There it is. Okay? Here's 3 quantum numbers that we use to describe this orbital. We just learned that in this orbital, how many electrons can there be? 2. Only 2. So I'm going to draw a dot here to represent one of those orbitals, or electrons, and I'm going to draw a dot here to represent that electron. Okay? If we're assigning a value to a specific electron, each of these electrons is in exactly the same orbital. So that means that the first 3 quantum numbers are exactly the same. But we have to tell those 2 electrons apart. And that's where the spin quantum number comes in. How many values can the spin quantum number have? Only 2. So we can assign this electron a +1/2 value and this electron a -1/2 value. The only time we would get to the spin quantum number to distinguish things from each other is when we're talking about the same 2 electrons in the same, or sorry, the 2 electrons in the same orbital. Okay? All right. Tonight's quiz gets you a little bit into shapes of orbitals and assigning quantum numbers. It will become active right at the end of class today. I highly recommend that you do it tonight and get it done. All right? Say it? Yeah, we'll give you your score right away because it's all multiple choice. Okay? Hey, I'll post this recording a little bit later on, so if you need to go back and take a look at it before you do your quiz, it'll be there for you. Tomorrow, we start orbital diagrams, and orbital diagrams are a little easier than this.